We use the laws of refraction to to deduce the angle of deviation delta in a prism. So this diagram shows a prism. Let me try to draw a bigger version here. So that's a prism that we are interested in. That's it. The angle that the prism makes is given to be 50 degrees. It's not an equilateral triangle, so that's angle alpha. That's 50 degrees. So let's choose this to be our reference point where we have the normal uh, ray. So let's say that's our normal line. So that's reference line. So that's normal line. Okay. A ray of light comes incident at I1 is equal to 45 degrees. So that's your 45 degrees here. And it's pretty much bisecting that angle. And that's your, let me make that in red. So that's my incident. Right. Light should go in a straight line if not for the prism, and that line represents that straight line. Should go along that line through the point S in there. But instead it gets refracted. And in this particular case, we will see that this actually gets refracted to uh, exactly parallel to the base. But that doesn't have to be the case. It could also be refracted in this manner here. But in our scenario, it will turn out that it's pretty much parallel to that. So let me draw it like that to begin with. But again, caution is that it is this line need not be parallel to that, but only for a particular incident angle that happens. So my incident ray comes at an angle of incidence I1, which is given to be 45 degrees. And after refraction, it is no more I1. I1 is this angle here. Right? That's my I1, but it reduces, and that's called R1. Right? I can calculate that R1. Let me calculate R1 here. We have the refractive index outside the prism. That's the refractive index of air times sine of the incident angle. I1 is equal to refractive index of the glass, in this case the prism, times sine of the angle of refraction, that's R1. That's 1.0 to 2 sig digits. Sine of I1 is sine of 45 degrees. And refractive index of glass is 1.5 and sine of R1. This lets us solve for R1, and we get R1 is equal to the sine of 45 to begin with. So sine of 45 degrees, so that's 0.707, 1 over root 2, basically divided by 1.5, that's 0.47, but we have to take inverse of that, and that's about 28 degrees. So it's not really parallel, it comes out close to being parallel, so it's about 28 degrees. So R1 is 20 to 2 sig digits, it's 28 degrees. So again, let me check on this. So it's sine inverse of sine of 45 divided by 1.5. Now that's 28.13. So if we do six digits, that's 28 degrees. That's good. So again, I said this will come out exactly parallel. No, it's not. It is actually 28 degrees. If this is 28 degrees, the rest of it is not 60 degrees, it's 62 degrees. And we'll see that it will not come out to be the same. Okay, so now we are sure that this is R1. So let me actually raise this a little bit and make that clearer. So this is actually 28 degrees and it doesn't have to be parallel. So that clarifies that it's not parallel. Okay, raise this angle. Oops. Bad. Okay, try this again. So that's my ray, and this is R1, and I1 will be this angle here, original angle, which is exactly, so this is I1. Okay, our I1 is 45 degrees, R1 is 28 degrees. At this point, again, I draw a normal line. So it's my normal line, and it's 90 degrees with respect. So it's 90 degrees. Okay. So again, clarification that this is actually 90 degrees, which means, and this is another normal line, that's 90 degrees. Completing the ray diagram, uh, light reaches here. It would like to go straight. If not for the interface, it would have gone this way, but this time it bends away from the normal, and that's given by that. It goes away from the normal, and that's your. And if I were to project it backward, I think it's better to project it using. So that's my projection in the backward. So the ray itself goes there. And this angle, where originally it should have been going in this direction, but instead it is going this way. The angle between the original angle of incidence and the final angle of refraction is the angle of deviation. So that's angle delta. That's what we're interested in calculating. We have calculated R1 of the, if we have to calculate this delta, we should be able to do something at the refraction at the second interface. But to get the original incidence angle there, which we will call R2. But R2 is related to R1 if we know this angle. And for that purpose, we take a quadrilateral. So this is A, P, Q, and R. So in the quadrilateral, uh, A, P, R, Q, the total, the sum of all the angles in the quadrilateral is 360 degrees. Let's call this angle theta. And what we have is actually I am interested in, yeah, let me see. So angle, so angle theta plus, what is this angle here? Let me do that in black. So that's 90 degrees with respect to the green line, that's 90 degrees. And the same thing works here. So that's 90 degrees because it's a normal line. Normal line makes 90 degrees. So as far as angle A goes, it's alpha. Angle P in the quadrilateral APRQ, so this is a quadrilateral, alpha plus 90 degrees here. And then angle theta plus the fourth angle is 90 degrees again, and altogether this amounts to 360 degrees. Angle alpha is given to be 50 degrees, so that's 50 degrees. So overall, we can calculate angle theta using this. So theta comes out to be equal to 360 minus 180, 90 plus 90, that's 180, 180 minus 50, so that's 130 degrees. So that's 130 in here. Once we know the angle theta, we can actually calculate angle R2 because R1 plus R2 plus theta is in the triangle, right? So in the triangle PQR, what we have is angle R1 plus angle theta plus angle R2. This all three should be equal to 180 degrees, which means angle R1 was 28 degrees, theta is 130 degrees, plus R2 is equal to 180 degrees. So that makes it 50 minus 28. So R2, this implies that R2 is equal to 22 degrees. So we know R2 here. Once we know R2, we can calculate the angle of refraction, that's I2. We'll call that I2 here, which will be the same as this angle here. Oops. So let's say this is angle I2 and R2 is actually this one here. So I2 is the full angle here, so it's up to, it is the across the interface. Use law of refraction there. This time it's going from the prism, which is the refractive index of glass, times sine of R2 is equal to the refractive index of air outside times sine of I2. Plug in the numbers, so it's 1.5 times sine of 22 degrees is equal to air is 1.0 times sine of I2. So this allows us to calculate I2. So I2, this implies, right? This implies I2 is equal to sine of 22 into 1.5 and sine inverse of that quantity. Now that's 34.2, so it's 34 degrees. So I2 comes out to be 34 degrees. That's great. So now we have I2 in here, so that makes it, uh, we have all the information in the quadrilateral SPQR. So let's have SPRQ. So that's a quadrilateral. And in that quadrilateral, let's start with the angle S, which is 180 minus delta, plus the angle P in the quadrilateral, that's I1. Is I1 because the dotted line here is the projection of the incident ray, and the incident ray, the angle between the incident ray and the normal line is I1, plus angle theta, which we have is 130 degrees, plus I2 here again because the angle between this dotted line and the normal line is the same as the angle refracted, uh, angle between the refracted ray and the green line, and this dotted line is nothing but the refracted ray traced backwards. And all these four angles together, since it's a quadrilateral SPRQ, should be equal to 360 degrees. This allows us to calculate delta. So delta is 180 minus delta plus I1, we said is, I1 is what is given. That's 45 degrees plus theta we calculated is 130 degrees plus I2 we calculated is 34 degrees, which overall has to equal 360 degrees. So this implies that 180 plus 45 plus 130 plus 34 minus 360. This leads us to an angle of deviation equal to 29 degrees. That's delta, so that's 29 degrees. Again, it's involved a little bit of steps, but at each point we are just barely using law of refraction and the geometry of a triangle. Let me stop sharing here and let me stop the recording.